In this video we're going to look at lifetime assessments of the environmental impact of a product. If we think about cars for a second, we often look at cars, or people often look at cars when they're purchasing, and they look at how efficient they are, how many miles per gallon a car does. And that's important, of course, because the more fuel a car burns, the more carbon dioxide and into the atmosphere, and therefore possibly the more pollution, and that drives the way some people buy cars. However, what we really need to be thinking about is, if we're interested in doing things in the best possible way for the environment, is doing a lifetime assessment of the product. Now, a lifetime assessment looks at the environmental impact, not just of using the product, but of manufacturing it. Sorry, not just of manufacturing it, but of obtaining the raw materials for manufacturing, the manufacturing of the product, then using the product, and then finally, once we've used it, the disposal of the product. Now, when teaching this in class, I show a little video clip of Top Gear when Jeremy Clarkson was on Top Gear. Now, he may not be your favourite presenter, but he did a clip about the Toyota Prius and how everybody thinks that's environmentally friendly. Now, Toyota Prius, if you don't know cars, has a battery engine, but a battery motor for when the car is in town or going slowly, so that's electricity, so there's no emissions. And then when it speeds up onto the motorways, it has a small petrol engine to make it go faster. Now, of course, what you have there, and people are buying that because they think it's more environmentally friendly, but what his argument is, what you have there is you have two sources of power for the car, and they both need to be manufactured, and they both need raw materials. So though the car, while using it, may be more fuel efficient, it's not more fuel efficient in terms of its manufacture. And he goes far to talk about the nickel in the batteries. He says it's mined in Canada, which is, to use his words, a filthy business with lots of acid rain, when it's then refined in Europe and manufacture continues in China. And of course, this nickel has to be shipped all over the world, lots of CO2 emissions in that. And then finally, it's put together in Japan. So it's a hugely intensive business manufacturing one of these cars. So to summarise, for the life cycle assessment of a product, we need to take into account the raw materials of the product. Okay. The environmental impact of all aspects, but particular, I suppose, of the mining or the sourcing of these raw materials. So that's mining and processing. And the energy and the energy usage. For example, obviously mining requires us in open cast mining for a lot of metals. We have to dig and scoop these minerals out of the ground, and there's obviously huge amounts of energy for the plant needed to do that. And then there's the manufacturing. Manufacturing requires huge amounts of energy and land and transport. So energy, land, and transport. I'm not sure many people want to live next to a massive manufacturing factory. And then the use. This is the one people mainly think about, the use of the product. So we're interested in the energy efficiency. How much energy does it need, and what impact does that have on the environment? Also, how much pollution is caused. And pollution can be, of course, atmospheric pollution. I suppose that's the one a lot of people think about. But, in terms of cars, noise pollution, or aeroplanes, noise pollution. If you live next to an airport, you want quieter airplanes. So that has to come into it as well. How much pollution is caused. And then finally, of course, the one that a lot of people forget about, disposal. When the product has come to the end of its life cycle, can it be recycled? What are the environmental issues about recycling the product? If it can't be recycled, how much landfill does it cause? The one I often like to talk about in lessons here is nuclear power stations. Some of the nuclear power stations in the 1970s, 1960s were seen as brilliant at the time because they created or generated electricity with no carbon dioxide emissions. Having said that, once they were decommissioned, the spent fuel needs to be processed Now, in some cases, they're still sat. The spent fuel is still sat in sheds on the site of these nuclear power stations because it is still so radioactive 30 or 40 years later. Likewise, the radioactive core of the power station is still there. It's still big concrete buildings because they're still so radioactive. So there's still energy required to maintain these buildings, and the visual pollution of them being on the horizon. Okay, let's quickly do also here oxidation reduction in its simplest terms, because we've been doing about metals. So oxidation is gaining of oxygen in its simplest term. And reduction is loss of oxygen or losing oxygen. Now, so for example, when we dig iron out of the ground as iron ore, we have to reduce it to get the oxygen away from the iron so we can use it. So let's look at this in terms of metals now. So we've got a reaction here. Magnesium and oxygen makes magnesium oxide. So in this reaction, the magnesium was gaining oxygen, so that's going to be oxidised. So you need to go down each of these doing this for every one of them. So in this case, aluminium oxide is turning to aluminium and oxygen. The aluminium oxide is going to lose the oxygen, so the aluminium oxide is reduced. Okay, let's quickly go down to these last two here. The iron oxide being heated with carbon. Well, if we do that, the carbon is going to take the oxygen, it's going to create ions. The iron oxide is reduced. Now in this case, we've got the same example here, the iron oxide being heated with carbon, so it's exactly the same example. In this time we're talking about the carbon. The carbon is going to take the oxygen, so the carbon is going to be oxidised. Okay, and what that shows here is every reaction is not reduction or oxidation, it just depends what we look at. Okay, and so we actually call these reactions redox reactions, reduction oxidation reactions. So we've come across this definition before with electrolysis. A better definition of oxidation and reduction involves gaining and losing of electrons. The phrase oil rig can help you remember it. Okay, so oil rig, oxidation is loss. Okay, oil of electrons. So when we're doing this oil rig definition, okay, and we're talking about electrons, reduction is gain of electrons. And of course that's the reverse of the oxygen one, isn't it? Oxidation is gaining oxygen and losing oxygen. But when we're talking about electrons, reduction is gain of electrons. And that's our metals unit finished.